Thank you. Thank you. Hi, everyone. Let me share my screen and we'll get started. Okay. Well, everyone, I hope you're ready for some more ZO content. I don't think we've had enough of that today. So thank you for the introduction, Shannon. My name is Itamar. I'm a principal architect at ZyVerge, and I'd like to talk today about ZO's streaming library, ZStreams. I'm pretty excited about that. We've had some important improvements to ZStreams, so I'll walk you through those. And what we'll touch on in this talk are some common patterns that I've seen that show up in applications that are pretty elegantly solved using streams. Okay, so what exactly is a functional stream? Well, we've seen today that a functional effect is a description of a program that needs an environment of type R to be executed. It may end with an error of type E, and it may end with a value of type A. Now, the important part about functional effects, especially like ZO, is that when they end, it's either with an error or with a value, and it's exactly one value. There is no optionality here. There are no multiple values. It's always exactly one value. So a functional stream is pretty similar. It is a description of a program that requires an environment of type R to be executed. It may signal errors of type E, and it will yield, and this is the important part, it will yield 0 or more values. So ZStream, which is ZO's description of a functional stream, it can represent an empty stream, right? We can execute a stream, it might end up empty. It can represent a stream with just one value, or it can even represent a stream that never ends. Like it's an infinite stream. For example, if we're polling a Kafka topic or reading from a socket, there is no inherent definition of an end there. It may at some point arrive, the end of stream signal, but it might as well never arrive, and we're dealing with an infinite stream that must be interrupted from outside somehow. Sorry. So that's the essence of a functional stream. It's a description of a program that could emit at any point 0 or more values. Another important part is that these programs could execute functional effects as we walk through them, as we pull elements from them. All right, so this is leading up to evaluation of a stream. What is exactly evaluation of a stream? Well, we know what is evaluation of a ZO program. An evaluation of a ZO program is just executing its effects, right? And getting back the error or the value. So with streams, it's a bit more complicated. We first need to somehow translate a stream, a Z stream, into a program that represents a functional effect. So with ZStream, we have the convenient run function. That's right here. The run function says, let's set up a process that will continuously pull elements from the stream and feed them into something called a sink. So sinks are ZStreams' mechanism for collecting values or collecting results from a streaming program. So what we've got here is a stream of strings of A that is repeated forever. So this is a stream with one element that is repeated forever. So that's an infinite stream right there. And what we're doing is collecting all the elements coming out of that stream using sync.collectAll. So this is a sync that will collect all elements in a collection, in a strict collection. And what we're doing here is we're running the stream into the sync, and this translates the ZStream program into a ZO program that will yield a list. It's actually going to be a chunk in the next version of ZO, but right now this gives us a ZO program that returns a list of string. So syncs are the way for us to compile down ZStream programs into Zio programs that we can run and evaluate. Okay, so let's imagine that this thing right here is representing a file descriptor. So if we're operating on individual elements, let's say every element is a byte from the file, this is going to be pretty slow because we're working byte by byte and pushing every byte into a list. Well, that sounds terrible in terms of performance. Bytes are not meant to live outside of arrays, right? Bytes should always live inside an array. The worst part about working element by element is that we're boxing the bytes. So we're almost tripling the amount of allocations that we're doing. Well, that's bad. So in the last version of Zio, from RC19, we've added chunks into streams. So from now on, every time we're working with a stream, we're always working with chunks. There are no streams with individual elements. These streams always use chunks. So every time we evaluate the stream, we pull an element out of the stream, we're actually pulling out a chunk of elements, right? So we'll see why chunk is good in a moment, but sorry, conceptually, this is great because all the I/O in the world, all the I/O subsystems in the world work with batches. You never read a single element. You never read a single row from a database. You never read a single byte from a file descriptor. You always use multiple elements. So for example, if we're calling an HTTP server and we'd like to read the response, we always read multiple bytes from the socket. And the same thing for file descriptors, right? We never read a single byte from a file descriptor. We always read multiple bytes or multiple kilobytes even. And this is great because the default block size for most file systems is 4 KB or even larger for some file systems. So we're doing the right thing here by always working with chunks. Even JDBC drivers, most JDBC drivers will always prefetch a number of rows. You'll never work on a single row when you're working on result sets. The JDBC driver will always prefetch a number of rows. So this is great, and you don't have to do anything to benefit from this. From the last version of Zio, chunk is baked in the ZStream. You're getting it. You're getting the benefits right now with minimal code changes. So a bit about chunk. Chunk is Zio's immutable array-backed collection for streams. We wrote it initially for ZStream, but it has evolved into a very attractive general collection type. So it's an immutable array-backed collection. We try very hard to always back chunks by arrays, but if you'll give it a vector, it will keep the elements in a vector. And most importantly, it tries very, very hard to keep primitives unboxed. This is super important for efficient processing of files, of sockets, or doing HTTP servers, any sort of I/O work. You gotta keep primitives unboxed. And other nice attributes are O1 concatenation slicing, and we've recently added extremely fast single element appends. They consistently beat vectors in single element appends. Great feature that Adam added. So chunks are very attractive as general collection types. I think we'll see more of them in Zio's general API. But ZStream uses chunks throughout. You don't have to do anything. It's all chunks. So what sort of superpowers do we get by using streams? Well, this is a snippet of code that reads a file into a string, splits the string on new lines, iterates over the lines and prints them out, right? Pretty simple, pretty easy to read, pretty simple to understand, nothing special here. Well, the only problem here is that if we try to run this on this sort of file, an 8 gig CSV we've received from a client in our ETL systems, well, that's not fun, right? That's not going to work. It's going to try to read 8 gigs of bytes into a string. That's not going to work because arrays can't hold 8 gigs of data. And that's just going to crash. Well, instead, we could just use streams, right? This is the same functionality. We're constructing a stream from a file, okay, with a chunk size of 16 kilobytes, transducing all the chunks. Transducing is a fancy word for stream transformation, by decoding the UTF-8 bytes and then splitting the lines. And then we just print out every line that passes through. We can actually, I discovered recently that you can actually even write it in this form, but that's just trivial. So this does the same thing. It does it in bounded memory. And most importantly, I think, is that this sets us on the path of easily evolving the application, because I mean, once we have this stream, the type for this stream here is a stream of strings. Each string is a different line in the file. Now, once we have a string of strings, it's pretty easy to start composing it with other transformations or compose it with different streams. And ZStream provides extremely rich compositional opportunities. How rich? Well, this is a word cloud I generated of all the operators on ZStream currently. Now, well, I can assure you that if you think of a way to compose streams together, there's an operator here for this, right? Just like there's an app in the App Store, there's an operator on ZStream for composing your streams together and transforming them. You'll find anything you'd like. Now, in particular, these streams excel at very expressive control flow. So for example, we can take a bunch of streams and merge them together using the merge all operator to get back a bigger stream that contains a non-deterministic merge of all the elements from the streams. And then we can, I don't know, partition them using some sort of predicate function to send elements that, that answer the predicate up here and the rest down here. We're still operating on streams, so it's all lazy, it's all functional, it's all pure. And we can take those two streams, we can take one of them, we can group it using some sort of keying function, and take two of the streams and, I don't know, zip them together, pairing elements pointwise between the streams. It's very cool. Now, this is all very nice, but the most important part is that we're doing all of this while maintaining resource safety, right? Everything is safe here. We can easily use these operators to create programs that declaratively specify how their concurrency patterns while keeping things resource safe, leak free, and very, very efficient. And this is really a joy to write programs in this way. And this is what really excites me about streams. So what are some, I don't know, red flags we should be watching out for? I mean, a stream a day keeps the doctor away. That's what I say to the teams I'm working with. What should we be watching out for in our code that signals that we should be using streams? Well, it's very common to use the for each bar n operators for parallelism. So what we've got here is a snippet that operates on a list of numbers. It tests each of them for primality using the isPrime method. And it operates on these numbers, 20 numbers at a time. Right, so up to 20 invocations of isPrime in parallel. Sorry. After that's done, what we'll be doing is some more hard work. It's not very, it doesn't really matter what's happening here. This also happens in parallel, and then we're done. I guess this is some sort of cycle. Now, the sad thing about this snippet is that we'll be waiting for all the numbers to be tested for primality before we even start doing any of the hard work on any of the numbers that have finished, which is a bit of a shame because we're wasting resources here, right? When we reach the end of the list here, there'll be like one or two numbers that are left. We could be starting work on this part. So what we've lost by doing this work this way, we've lost pipelining. Pipelining is a very important part of of modern applications, which is a shame. But no worries, we can just rewrite it even more succinctly using ZStream. So we just take all the numbers, stuff them into a stream by using the from iterable constructor of ZStream. And we use the map and par operator, which says, we'll run this function up to 20 times in parallel on the elements that are coming in. And this is automatically pipelined. So the numbers that have been tested for primality will immediately reach here and start working. So this is pretty nice. It's pretty succinct. It's very declarative. It's easy to see what's happening here. And it's even shorter than this snippet. So how could you do that? Another way to solve this sort of pipelining problem that is very tempting, I admit, is what I call fibers and queues, stringing up a bunch of fibers, a bunch of lightweight processes with queues that connect them. So we've got 3 queues here. We've got a fiber that writes to the input queue, a fiber that copies between the input and the middle, a one that copies between the middle and the output, and one that prints the elements from the output queue. This should be the output queue, sorry. So this is pretty tempting, and it's pretty straightforward, I guess, to write this sort of program. The problem is that we're in actual programs we're definitely not getting interruption rate, because there's usually a particular order in which if we want to terminate this computation, this running computation, we should be terminating the computation in a particular order. We should first shut down the input, then this one, then this one. Well, this is hard to get right using fibers manually. And even worse is that we don't have any sort of functionality for graceful shutdown here. I mean, we want to shut down this fiber and then drain all the queues. And once they're empty, we want to shut everything else down. This is hard to get right. And ZStream does all this for us. So we can rewrite this in this fashion. We can use repeat effect to generate elements, introduce a buffer between each processing step, and then finally print the elements. This is interruption safe, it's pipelined. It can use repeat effect option instead of this constructor to create the graceful shutdown functionality. It's very easy. It's very declarative. I like this much more obviously than this, and it's shorter. You know, these things, these solutions with streams tend to be shorter, and it's all safe. So these are some red flags you should be watching out for, and these are the killer use cases, right? If you're dealing with file socket IO or any sort of messaging queue like Kafka or RabbitMQ or any sort of other queue, or you're dealing with databases and you're fetching results sets, or you want to do some sort of concurrent processing in a declarative fashion and not tear your hair out dealing with interruption and whatnot and deadlocks, well, streams are definitely the answer. All right, so we've seen the red flags, we've seen the killer use cases. Let's see a few common patterns that show up in applications that are super elegant to solve using streams. Okay, so first off, meet RabbitMQ. RabbitMQ is a pretty popular message broker. It's pretty efficient. It has lots of features for routing messages. It's a pretty good message broker. Now RabbitMQ recommends that its Java driver, be used in push mode. So you're not pulling for messages. You're not pulling the broker for messages. You'll be registering a callback that will be called once there's a message available for our consumers. So what we're doing is we're doing channel basic consume. This means I want to register a consumer that will be called when there are messages available. And this consumer has 3 callbacks: handle delivery, when there's a message, handle shutdown, handle cancel. And RabbitMQ will call us or call the driver when there is a message available. Okay, so we've done that. Our main thread continues down here. Now what? We need to do some sort of processing for the messages. So what should we do? Should we like stuff all of our logic into this callback? So everything will be driven by the callback from RabbitMQ. So we'll do the deserialization here, dispatch to whatever component in our application that needs to deal with the messages. Well, I don't like it, right? It's like we've turned around all the layers of our application, push them into the callback, and then it's driven from here. Well, it doesn't look scalable in maintenance, I mean. So what else can we do? Well, I guess we can enqueue the message somewhere into some sort of internal queue that something else is consuming from, another fiber. Well, this is getting there. I think this is the right path. The problem again is handling all the edge cases. Like what happens when we want to shut down the application? We need to first unsubscribe the consumer, then we need to drain that queue, then we need to shut down the rest of the application once the queue is drained. Well, it's hard. And this is not fun. So the ZStream solution for escaping multiple callback hell is called ZStream EffectAsync. It's pretty similar to ZO.EffectAsync if you've seen it. It's a way to integrate with callback-driven APIs, but the difference from ZO.EffectAsync is that ZStream.EffectAsync works for callbacks that occur multiple times. So the callback for ZO.EffectAsync is meant to be called just once. For EffectAsync, it can be called multiple times. And under the hood, it uses queues. It does all the ugly things that you might expect it to do, but it hides it. It hides all those ugly things from us users, allowing us to remain in high-level composition and use all the nice things we know from streams. So what we're doing here, we're calling EffectAsync. We need to specify the types currently. And this callback here, this is what we need to call whenever we have a new message available. This is our queue.offer. So we'll register our consumer. And what we're saying is whenever there's a message available, call the callback with the body of the message. The interesting part here is that we can also handle shutdown because this is essentially a callback that can be called multiple times. There is no indication here to how many times it should be called. We need to somehow signal from inside this code that we're not going to call the callback anymore and the stream should be shut down. So what we're doing here is that we're failing with a none. Right? This is something afforded by ZO's typed errors functionality. We can fail in quotes with any sort of error, and this becomes another way to transfer information to our stream without encumbering the type of the value, right? So what we're doing here, we're failing with a none, and none signals to the stream, well, you should shut down. We're not going to call you anymore. So what we'll get from the call to EffectAsync is a plain old ZStream of byte arrays, which we can freely compose as usual, and we don't have to deal with any weird callbacks or stuff all of our application inside. Just a plain byte array. That's great. And we can also register a cancellation mechanism that can be used whenever we interrupt the stream from outside, because we want, whenever the stream is interrupted, we want to unregister the consumer, so RabbitMQ doesn't think we still have a consumer registered. So we can tell the stream how to unregister its consumer when the stream is interrupted, which is very, very important for working with these sort of APIs. Okay, so that's multiple callback hell. How about batching? I mean, we've seen that for all sorts of I/O, batches and chunking are pretty important. And with streams, we can do user-defined batches, not just the underlying chunks, but we can do user-defined batches pretty easily with something called group within. So group within will collect elements into a list up to 2,000 elements. And if we've got less than 2,000 elements and 30 seconds have passed, it will pass whatever it has collected, even if it's 0 or 1, down the stream. So this is a sort of timeout for the aggregation. Now, group within is a shorthand for this operator called Aggregate Async Within that uses a transducer. Transducers are again stream processing functions. It's kind of outside the scope of this talk, but transducers are ways to aggregate elements over a stream. And it uses Zio's amazing schedule data type that describes what's the schedule for the timeouts. Okay, so that's great. Well, we're taking this data stream, aggregating it to lists of 2,000 elements every 30 seconds. Awesome. Well, what now? What happens if we'd like to balance throughput and latency in our stream? Well, this approach aggressively favors throughput because it will introduce a fixed amount of latency into our stream. We will always wait for up to 30 seconds if we haven't reached this sort of boundary value. Well, instead we can use aggregate async. This operator will ship things off downstream as soon as the path is clear. So if map M is not already processing a previous batch, then aggregate async will just ship off whatever it has over it, even if it's one element. And we can even construct something a lot more sophisticated thanks to schedule. So what we're doing here is that we're creating a schedule that operates on lists of records. What the schedule does is it starts off with 30-second timeouts for as long as its inputs have a size that is lower than 1,000. Now, once we see an input that has a size higher than 1,000, what we'll do is that we'll switch to a shorter schedule with some jittering, and we will remain with this schedule for as long as the size is over 1,000, right? So now, once we have this schedule, we can pass it over into aggregate async within, and now we have a much smarter adaptive batching algorithm, which will adjust the amount of timeouts it will be introducing as a function of the rate of the stream. This is pretty cool. This is pretty cool, and you can and the possibilities are almost infinite using zschedule and ztransducer. It is a very sophisticated mechanism that is baked into ZStream, all available for your use. So that's adaptive batching. The last pattern I'd like to cover is something that has come up a bunch of times in Zio's Discord, and this is application composition. It's a much higher level concern. So usually microservices or long-running applications in general are often composed of a bunch of components that need to be running infinitely in the background. And if something happens to them, if they crash or they terminate abruptly, we should be crashing the entire application. So what our main fiber should be doing is it should launch all of those background components and wait infinitely. It should not exit, because then our application won't be running. We should launch all of the background components and wait. It should interrupt everything, all those components, whenever we receive a termination signal from the operating system. And it should watch all of those fibers, all of those background components, and quickly exit, like crash quickly, if something goes wrong. So how should we do that with our main fiber? Well, here's an approach that doesn't work, right? We can launch the Kafka consumer and fork it, launch the server and fork it, and launch our scheduled job runner and fork it, and then wait. So, I mean, this will indeed wait. But if something happens to any of them, if they crash, then nothing happens, right? then our application just hangs and remains up without anything working in the background. Okay, so maybe we can watch the fibers somehow, right? So we'll switch to using zmanaged. Zmanaged is also outside of the scope of our talk but zmanaged is usually useful for top-level application composition because you usually want to acquire and release resources, which is what zmanaged does. So we're forking fibers using zmanaged, which means that they will be interrupted as part of the release action. And then what we're doing is that we're racing all of the await functions for those fibers. So what this means is that as soon as one of those fibers terminates with either an error or a value, because I mean, these should never end, right? Even with a successful value, these should never end. They should be running infinitely. As soon as one of these ends, it will interrupt all the rest. So this is nice, but it has a bunch of problems. First, we have to name things twice. That's always a bad sign. We need to unwrap this Kafka consumer and call it Kafka. And we have to specify everything twice. What if we forget we add another component and we forget to add it here? That's bad. So instead, we can use streams. We can imagine all of those components as single element streams that never end. And we will be merging all of them together to a single application, to a big stream that represents our app. And whenever something happens to one of them, it will emit the error and crash the big stream. So it looks kind of like this. We use the merge all unbounded constructor from ZStream. And this does everything we wanted magically. I mean, not magically, it's just code, but it does everything we want. It's super elegant. Whenever we add another background component, we just add it here. Super easy. That's it. That's it for my talk. Thank you for listening. If you like to learn more, I'm giving a course about stream processing with Scala with ZStreams in June. It's remote only, convenient time zone. Scan the QR code and you'll be led to the Eventbrite page. And thank you for listening. It's been fun.